Yes, great. So thank you everyone for attending today's Future Intelligence talk. Today we are happy to have Dr. Li Fu she is an assistant professor from the University of Surrey in the psychology department, which is quite interesting for us. And today she will introduce her research in the human robot interactions, and then the floor is yours.
Okay, thank you so much for the invitation and nice introduction from Yue. And hi everyone, I am Dee, and I'm currently I work as an assistant professor in both psychology and AI center at the University of Surrey. And today I'm very happy to share my work with you. And my topic is about social cues integration in cross-modal human-robot interaction. So at first, I would like to introduce a bit about my education background. In 2014, I entered the fast-track PhD program at the Institute of Psychology, Chinese Academy of Sciences. And back then, I focused on cognitive neuroscience, especially attention and cognitive control. So in 2017, I exchanged to the Department of Computer Science at the University of Hamburg, Germany, to set up a project collaboration with them. My research direction shifted to cross-modal learning and human-robot interaction. And after I finished my PhD in 2020, I continued working in the same computer science group as a postdoc researcher and focused more to be like cross-modal social cue integration and its application in human-robot social interaction. And this year, 2024, 10 years after I started my research career, I moved to University of Surrey, UK, to become an assistant professor and an independent PI with a focus on HCI combined with cognitive neuroscience, as well as expanding my research into games applications. So lots of people ask me this question. As a psychologist, why do you want to study about human-robot interaction? So the first reason is, I guess many of you like me, we were born in 1990s. So we happen to live in this era full of thriving AI research. No matter from Deep Blue to ChatGPT, AI and robotics always surprise us and impact our life a lot. And the other reason is I am especially interested in social robotics. Social robots are becoming very widespread in our daily life. For example, in education, also in like humans' well-being, we can make the robot to work as a life coach and to talk to people, and also we can make the robot to work in, for example, to work as a caregiver, to play with the elderly, and also we can make the robot to interact with some kids who are suffering from some mental disorders or like ASD or ADHD. So my study mainly focuses on social integration and attention, as I introduced before. So for example, in this figure, we are sure that the theater now is on fire, right? However, you can see that this lady, she is looking to the right, but running to the left, which is contradictory to the others, right? So if you are the man in the bottom of the right corner, do you know where to run? And what if we have robot fireman? How can it process and deal with the conflicts between different social cues? So my studies try to investigate the following questions. The first is, how can a human-not robot perform human-like attentional behaviors in such kind of complex environments with cross-modal conflicts? And the second one is, what is the impact of multimodal social cues displayed by human-not robots on human-robot collaboration? And the third one is, how do humans perceive a human-not robot delivering mirroring behaviors of human social cues? And the last one is, how can a human-not robot interact with humans by integrating different social cues and exhibiting different personalities? So my study is from a low level to a high level, but it's basically about cross-modal conflict resolution and social attention and human-robot interaction. Okay, so here is my first study. So I want to know whether deep learning techniques can make the robot deliver human-like social attention. So for example, psychological studies show that social attention helps infants who cannot talk learn their parents' intentions and build social relationships with the others. So we know that the standard paradigm used to study social attention is called the gaze cueing task. So participants are asked to determine the position of the target. Before the target, there is a gaze cue, which could be spatially incongruent or congruent with the target. And participants always have slower and less accurate responses under incongruent conditions than under congruent conditions. And in HRI, researchers also found that mutual gaze between humans and robots could delay humans' decision-making. However, is it the same under a cross-modal situation? And can any deep learning model make robots display real human-like social attention? So this is my interest. And here is the scenario we built for our study. Can play a little bit. Can you hear the sound? Can you hear the sound from my demo?
Not really.
Oh, maybe I have to share my sound.
Yeah.
Let's see, what can I do with it? Okay, let's try it again.
Hello.
Can you hear the sound?
Yes.
Okay, that's
Yes.
great. So in our study, we built a 3-avatar meeting scenario. So as you see, the middle avatar can switch his eye gaze to the left one or to the right one. And the auditory target could be spatially congruent or incongruent with the visual cue. And here you can see the auditory target is very simple. It's only one word, hello. So we find that this static avatar's gaze could actually trigger the reflexive attentional orienting effect. So which means participants perform much better under the congruent condition than under the incongruent condition. And here is how we make human participants to do the studies. So let's go back a little bit. So here you can see, for example, no matter reaction time or error rate, people always have worse performance under incongruent conditions compared to congruent conditions. And the difference here is significant, which means that our setup, although it's totally different from the traditional psychological paradigm, but this kind of synthetic avatar's gaze could also have the same effect on triggering humans' attentional orienting effect. Okay, so next, we build a deep learning model to simulate humans' attention. And we have a visual model here trained by a public data set of human eye movement. And also we have a binaural sound localization model. So here, the model of the fixation density map is used to predict attentional area for the robot. So we know that in the traditional HR experiment, people always they collect data from a bunch of people, and then they simulate their models based on the data they collected. But here we want to have some challenge for ourselves. So we train our model, our citizen model, on a public data set. So which is totally different from the task we use in our experiment. This topic data set is like a free viewing movie task. So they ask participants to wear the eye tracker and make them to watch a movie without any goals. So and the output is a typical density map. We want to know whether our model, our bottom-up model, can predict humans' attention. And here is our demo for the robot. There's no sound for this video. Yeah, as you can see that the robot can move its eyeballs to react to the stimuli on the screen. So yeah, it's very cute, right? But it's also a little bit creepy. So especially when we do the experiment, we find, oh my God, this is so human-like. But our robot doesn't have hands, so we make the robot to react to the stimuli by using the eyeballs. So as you can see that for the error rate, our robot has the similar pattern as human, which is under incongruent condition, the robot has worse performance compared to the congruent condition. So which means our model is kind of successful. But we find something interesting here. We find that if you focus on the y-axis of the error rate, you can see that the robot, actually the error rate for it is almost like 40%. But for human, their error is much lower. So how can we compare the performance between robot and human? So what we did is we use a typical psychological effect, which is called stimulus response compatible effect, which is used the income conditions performance to minus the congruent condition performance. So if the SRC effect is larger, shows that you have a worse ability to deal with conflicts in real life. So in this study, we can see that our robot, although with this powerful deep learning model, it can just deliver some human-like behaviors, but its performance is still actually much worse than the humans, which means that we don't need to worry about AI and robots that much. But our study actually still delivered in like 2021, 2022. So nowadays, the technique is totally different. Okay, so as you can see, my pre-study is about I use the model to simulate human behaviors and train a model on a robot, and then to make the robot deliver human-like behaviors. But also at the same time, I want to know if the robot has a human-like behaviors, or let's say social cues on its face or on its bodies, whether it can have some impact on human-robot interaction. So we can see that there are lots of studies about those scenarios. We have one human, we have one robot, and play games together. But I also want to challenge myself again. So I have one human and another human, and also a robot. We make these three, like say robot and humans, to play a game together. And I want to know whether the social cues, which are facial expressions and gaze on the robot, can impact this human-robot collaboration scenario. Okay, so here is our demo. So we have the robot here. The robot plays a role, which is called instructor. And the robot gives commands to these two humans. For example, please put the orange line into the sorter. And here we have an actor. The actor cannot touch anything here, cannot see anything here, but he can touch the objects or the sorter. And also we have a guide. The guide can see everything, but a guide cannot touch anything. So the guide has to help the actor to put the shape into the sorter as fast as they can. So let's watch the demo.
Already got it, perfect. And it's right above it. So you just have to turn the monkey bit and then shift it. Now you had it in the right orientation. You just move it a bit more, turn it a bit further. It's now tilted to the left. You turn it a bit more. Bit more. Bit more. Bit more. And now it should fit exactly.
Okay, bingo, they finished the experiment. So the interesting here is we actually don't tell the participants that why the robots have some facial expression change on its face and why the robots try to move the eyeballs. So we'll make the humans to guess the intention behind those robotic behaviors. So in this case, the humans could focus on both the game and also the facial expression change on the robot. So the pipeline here is, at first, we have initial facial expressions from the robot. This could be happy or neutral. And also we have initial gaze. It could be to the actor or to the guide. And for example, they finish the round and they put the shape in the right order. And if their reaction time exceeded 30 seconds, which means they are not very good at this game, so the robot is going to change its face to be sad and also switch the gaze to the other side. And if they are very good at it, they can play the whole thing within 30 seconds. The robot is going to keep their original facial expressions. And after each round, they press the button. So the button here have two functions. One is try to record their reaction time, and the other thing is about their perception to a robot. So here you can see S is for smart, which means they think the robot is intelligent enough, and X is not smart at all. So we have 10 rounds for each couple of participants, And after 5 rounds, they switch their roles and switch their sets. And we also have the Gatsby questionnaire for them. So our findings is very interesting for this experiment. So we find that the robot's initial happy phase actually can lead to participants' faster completion time than the neutral phase, which means if they face a happy robot, they can play better than a neutral robot, the robot without any facial expressions. And also we find that if the initial gaze from the robot is to the guide, but not the actor, then people think that a robot is more intelligent, which makes sense, right? Because the guide actually is the person who helped the actor to put the shape in the sorter. And also we find that the robot with the final happy face was rated more intelligent than a sad face, which means after they finish each round game, if the robot has a happy face, participants think, oh, it's really intelligent. So is it because that participants play well in the game and the robot has a happy face, so they think the robot is very intelligent? So we do a round by round analysis, and we find that actually it's not true. So you can see that here, people play better and better after each round, but their rating to the intelligence of the robot actually doesn't bother by their performance at all. So this is totally different. No matter they play well or not, they still can just judge the robot independently. And also, I have another video to you for you. This is about, for example, we make the robot to mirror human social cues, no matter the facial expressions or the eye gaze or the hand movement. We want to know that whether humans view this thing as a positive thing or a negative thing. So here is the demo.
In this study, we explored how humans perceive robots that mirror their social cues. For the movement mirroring task, participants wear an eye tracker and move their head and eyes at will. The iCap robot mirrors these movements in real time for 1 minute. Under one condition, a webcam captures the participants' movements, thus feeds into a model that estimates head orientation and guides the robot. We call this the vision-based method, demonstrated on the left. For the other condition showcased on the right, an IMU attached to the eye tracker tracks participants' head movements and transmits them to the robot. This is the IMU-based method. Participants try both methods, then share their impression of the robot through a questionnaire on trial completion. Our results showed that the iCap was perceived to be more responsive using the vision-based method in comparison to the IMU-based method. For the effective mirroring task, the Pepper and iCap robots mirror the participants' facial expressions in separate trials. Under one condition, the Pepper changes the LED colors on its shoulders and around its eyes in response to participants' facial expressions. The participants fill in the questionnaire after every trial to assess each robot's performance. For the other condition, the iCap changes the LED patterns on its face to mirror the participants' expressions as closely as possible. Each robot captures the participant's face using its own cameras and feeds those images into a facial expression recognition model that classifies expressions into 8 emotion categories. Due to the fact that Pepper expressed affect in the form of LED colors changes, it was viewed to be less human-like than the iCap. Our study shows that control methods and output modalities influence robotic mirroring in HRI, highlighting the importance of social affordances in robotic design. Thank you for.
Okay. So after studying lots of social cues, I want to know whether I can do some high-level studies. I want to know whether a human non-robot, after after integrating all the social cues from different modalities, can generate some human-like personalities. And then I want to know those personalities from the human non-robots, whether it can have some influence on human-robotic collaboration or not. So here we designed a very interesting game, which is called memory game. So we make human and play with human at first. We have participant. We also have we also have assistants. So our assistant have an extroverted one, and also we have introverted one. So we have like 6 cameras back then. We just record all the social cues from both players and also from the helpers or the assistants. So we labeled manually back then by using our own tool to say that, okay, this is what kind of social cues, and this belongs to extroverted, this belongs to introverted. And then we just simulate those features on different robots. So we have an extroverted orange robot, and also we have introverted blue robot. We can see how the robot play games with the human. Probably there's no sound. But we can know that actually the robot here, if it's extroverted, it has more actions. Actually, also it speaks faster than the introverted one. And you can see the blue one. Looks like a humble robot here, right? It also talks less than the orange one. So the interesting finding here is we figure out that actually, if we have 2 humans play the game, human enjoys playing a game with a person who has a totally different or opposite personality. For example, if I'm introverted, I want to play with someone extroverted, and then our game performance would be better than if I play with someone who is also introverted. But it's totally different from the human-robot interaction results. So we figure out the result between human and robot is totally different from human-human interaction. So human enjoys more to play with the robot who has similar personality, which means, for example, if I am extroverted, I prefer to play with a robot who is also extroverted, and my performance is better than I play with an introverted robot. And this is why, right? This is very weird. It is totally different from our expectation. And we look at lots of literatures and we find out that actually humans like to play with someone who is totally different from them because they think if someone is very different, they are more attractive. So they're going to engage more into this interaction. But when they play with the robot, they know the robot are machines. They hope the robot could totally under their control. So if they play with some robot which is similar to them, which means they can't understand the robot. They think the robot is safe enough to interact with. So this is a very interesting finding. And to summarize my research a bit, so yeah, my work actually is totally about social cues integration in cross-modal human-robot interaction. So I have, for example, experiment from this gesture study, gaze study. I have showed facial expressions and mirroring and personality. And the methodology I use is like behavioral tasks, modeling, and even eye tracking. And also we build some data set from the eye tracking. And we, for example, do some modeling work to predict the scan path here. And also we build a middleware, which is a wrapper, try to help people to run different social robot platforms and also like different machines together. For example, someone only know how to use ROS, but they don't know how to use YARP. And by using our wrapper, everything is easier for the users to use. So I think my research actually tried to make the robot display more human-like and more intelligent behaviors and more natural interaction with humans. And I don't want to only focus on the traditional way to do HR study, which is based on cognitive stimulation and questionnaires. So I want to use more scientific, more rigorous psychological experiment and deep learning techniques to make my human interaction studies more scientific. Okay, so here is the related publication I mentioned in the study. If you are interested in them, you can just go to my Google Scholar to look into more details about my studies. And yeah, now this is I moved to Surrey, and Surrey is really pretty. So if you are interested in my lab, you can come to have a visit anytime. And also we have this game project, which is sponsored by lots of game companies in Guildford, because Guildford is the game hub in the UK. So we're going to do some VR studies and also game studies with robots and humans. And I also put my WeChat QR code. If you want to contact me, you can also send me emails or just contact me directly by WeChat. Okay, before I finish my talk today, I also want to advertise a little bit about the workshop I will organize this year during the Roman conference. So we are very lucky to have two very excellent keynote speakers. One is Oya Sadik-Tutan and one is Alexandra Schutte from KCL and IIT. And they're going to give the keynote speech. And also, we are very lucky to get this sponsorship from Ducktown. So we're going to have we're going to select 3 top papers out, and we're going to offer people awards, no matter the DuckyBot or some monetary awards. And yeah, that's all. Thank you so much for coming today. If you have any questions, welcome. Thank you.
Thank you, Dee. It's amazing research topics. Please just unmute yourself if you have any questions.
I have a question for Dee.
Okay, thank you. Please.
Hi, Dee. Excellent speech.
Thank you.
I have a question about the robot personalities.
Okay.
Because I saw a few work about different personalities and people's preferences about different personalities, like robots being treated as children, or their cuteness is highlighted in many of the participants' responses. Do you have any comment on that when designing personalities in robots?
I don't have any experience actually in robot studies with kids, but I have done the study and also some studies on kids. So I cannot actually give you a direct answer on how robots with different personalities could impact kids and robot interaction. But for example, as you mentioned, like cuteness, I think this is more like a feature of the robot, which is not really like personalities we refer in psychology, right? So in terms of personality, usually we're talking about the big 5 personality, which is something like openness, extroverted or introverted, something like whether you are open, whether you are creative, something like that. But I think for robot, actually, robot is totally different from humans, right? Robot is still a machine. So when we talk about like personalities, we can have a more, a general like domain or different or general features to describe the personality of the robot. But yeah, this is the only personality study I have ever done for human-robot interaction. So yeah, probably I don't have so much more experience to share with you. But yeah, if you have more questions, I'm happy to contact with you later.
Yeah, that helps. Thank you very much.
Thank you.
For the email address, I can put, can they put your email address on the chat link so everyone can reach out?
Yeah, I can write it down now.
Yes, thank you very much. And in the meantime, I think I can have a really general questions to finish today's talk.
Okay.
Again, it's awesome because with the current scenarios around the world, the impact of robotics in our daily life is increasing crazily. So what do you think will be the most acceptable way for this kind of humanoid robot to join our daily life?
I'm sorry, I mean the impact way, right? Impactful way.
Impactful way and the practice way, because you mentioned for the elderly peoples.
Oh yeah, so we recently tried to do some studies with people who are suffering from dementia. So this is a possible direction, because that when people take care of those dementia people, they have to put lots of efforts into it. So we want to use our humanoid robot to help them to release some work. So for example, if we can make the robot really intelligent enough to help with people who have this dementia problem, so like take care of their life, help them, for example, do some daily work, that would be really useful. But it's still a very long way to go, because even for humans, it's very difficult to take care of people who have dementia. But the other direction I want to mention is education, because we have lots of teachers, we have lots of kids, but sometimes kids have different features, personalities, or they have like, we say neurodivergent problems, right? So we want our teachers, so usually it's like one teacher versus different kids or multiple kids. So it's not like every kids are okay with the way that the teacher teaches them, right? So they may have some complaints or they're not happy with the way the teacher tried to teach them. So we want to have the humanoid robots to work as the teaching assistant. So so for example, let's say we have this personality studies, we can also know that whether different kind of kids, they have different they prefer different teaching styles, or they prefer like different personalities, different teachers with different personalities. So this is our next goal.
Great, awesome. Thank you very much.
Thank you.
Yeah, yes. And if we don't have any further questions, we can finish out today's talk right here. And we will post today's presentation on YouTube soon. And also our next future intelligence talk will be in 2 weeks after. Thank you very much. Thank you everyone for attending today's talk.
Thank you.
And I hope can see you soon. Bye bye.
Bye.